right, so the first we are going to do is Fasta Format. So a Fasta Format is a text-based format for representing either nucleotide sequences or peptide sequences. So hopefully you have all encountered Fasta formats in some of your intro biology classes and some of the other biology classes that you've taken. But if not, it's a very straightforward format to know. So you have a name of a sequence. So a Fasta format stores some sort of sequence, and it stores multiple sequences. So it might store nucleotide, DNA sequences, or it might store peptide sequences. And so you have a name of the sequence, and the name of the sequence is preceded by this greater than character. So this greater than character is very important for indicating the start of a new sequence. And so it not only indicates the start of a new sequence, but it also gives you the name of it. So you can name your sequences. You can name it after a gene. You can name it after an organism. Kind of you're pretty free to do whatever you want. And then after that, you can have multiple lines. So it doesn't have to be a single line. You can have each 60 characters on different lines, and you go on and on until you reach the next sequence, which is indicated by this greater than sign. So the protein sequence is all this right in here, and then the DNA sequence is all this is right here. So we have two different sequences. So as an example of a FASTA file, we will cover the human genome. So this file is found in the example data that I published. And I originally downloaded it from here, the FASTA right here. This is the current version of the human genome. Note, though, that I reformatted this file a bit. So if you actually download it from here, you might have a bit of trouble to do exactly what we're doing, because there's some subtle differences in the compression scheme that is here versus what you need to have. So we have this file right here, and this is a Gzipped file. So this file contains the DNA sequence of 22 chromosomes, the X chromosome, the Y chromosome, and then it has a bunch of other sequences as well. So if you go to this website, you can see what is all in this file. So, you have chromosomes, and these are very large. So this is 248 megabases, chromosome 1. The X chromosome is 156 megabases. You have 57 megabases for the Y chromosome. So there's all sorts of different letters within this. And then there's also a large number of much smaller sequences. And these are a variety of different things. So a lot of these that are alt, these are kind of alternative haplotypes. So some parts of your DNA is very variable from individual to individual. And so it's so different that they actually store this as alternative DNA sites within this. Not very important for this part of the class so far, but just kind of for general knowledge. And then they also have, there's some pieces of DNA where we actually know the sequence, but we have no idea where it is. So we don't know if it's on where exactly it is on chromosome 4, because some DNA is so repetitive, it's really hard to place it in the correct place. So, we start to see why, originally this might seem very straightforward, to have a parser, to not need a parser. So why on earth would you need a specific parser in order to read this? It's very easy. It's a very straightforward file format. So you might think, I'll just write my own custom parser in order to do this. But now hopefully it starts to become obvious, because if I look at the size of this right here, this is a very large file. So this is actually a gigabase large file, and it's so large that we've actually compressed the file. So this gzip indicates that we've compressed the file. So we can't even look at this file. It's not a text file. It's this weird format binary file. And so if we try to look at it, we'd look at something crazy that didn't make any sense. And so some of these DNA files are so big that you probably don't actually want to read it all into memory, because depending on your computer, it might not have enough RAM in order to store all this information. So I'm going to remove some of this file, so we just have that this human chromosome like appropriate. So what do we want to use in order to read this? So there's actually a lot of different modules out there that can read in FASTA. We are going to use PySam. So PySam is useful. It's useful for next generation sequencing, so it can not only read in FASTA files, but it can also read in SAM files, and it can also read in VCF files, which are common file formats for next generation sequencing. So install this. So you need to install this using the following commands. Conda config. You have to add some of these channels, but if you follow this, it should be pretty straightforward to actually install PySam. And oh, shoot. And so I have a small bug in this line right here because originally I had this file stored in a different directory. But if you want to open it, you simply do this command right here, data equals PySam, and then it has a way to open FASTA files. So this is kind of this is a constructor that creates an object starting from a FASTA file. And so you notice now that it's still thinking, it's still taking a while to actually read in this file. And it's the reason it's taking so long is not that it's actually reading it all in. The reason that it takes so long is that it's actually creating new files. So you'll notice once you read this in that it created these 2 additional files. So these are called index files, and these index files are what helps it read the FASTA file very efficiently and fast. So it doesn't have to read everything in. But this is kind of details that might be a little bit lost. But so we open it up, and so now we have a object that contains all of the information, or the ability to read all of the information from this FASTA file. If you want to know the file name, for example, you can use this right there. And if you want to know the references, file data.references. These are the name of all of the sequences within the FASTA file, and then lengths gives you the length of all of the sequences within the FASTA file. If you want to actually access the data, all you have to do is it acts almost like a dictionary of strings. So you simply have to use the key is the name of the sequence, and then it returns a string, and the string is going to be very long, potentially hundreds of millions of characters long, and then you can just use the slicing operator to restrict it to certain parts of the DNA. So there you go. Now we can open a FASTA file, and we have this own custom object in order to manipulate the data if we wanted to manipulate the data. Just to help you orient, so you notice like chromosome 1 uses this particular name. So this is just kind of like the naming sequence that they use. This is it's called an alias, but you can see that chromosome 1, if you wanted to access the sequence for chromosome 1, you just have to use this sequence name right here. Chromosome 2, we got this right here, and so on and so forth. All right, so this is how you open a FASTA file. Hopefully that has been straightforward.